we call that linear question of other variables. So if imperfect, approximately equal, almost the same value, but not exactly the same. Okay. So this is an example for the case of perfect multi-collinearity when functional relationship exists among independent variables. So there is a given that is the sum of the combination of linear combination of linear independent variables equal to 0. For example, this one. So let's say x1 just like I mentioned just now. So x1 equal to -2 times x2. So exactly equal. So this one equal to -2 times of x2. So we have perfect collinearity between x1 and x2. So if multi-collinearity is perfect, then the regression coefficient of the x variables, the coefficient for the regression coefficient is this one, the regression coefficient beta 1, beta 2 cannot be are indeterminate, so we cannot identify the value, and the standard error SE are infinite. Okay, so that's the implication. Imperfect multi-collinearity when functional relationship exists among independent variables as given by this. So meaning that it's not equal to 0 but equal to an error term. So meaning that whether positive or negative. Okay, this one where V is stochastic error term. So as an example, similar to this one, but this one perfect is equal to 0, but this one equal to certain value, whether negative or negative, negative, positive, but it's also possible 0. It's also possible that certain value, some of them equal to 0, but some of them, the combination of x1, other value of x1 and x2 equal to either negative, positive, but they are almost similar values, so almost approximately equal. So then the regression coefficient poses for this case, for this situation, if we have imperfect collinearity, the regression coefficient poses the last standard error, which means the coefficient can be estimated but with less accuracy. So you can estimate, but the estimate is not accurate, so it's not reliable. They produce unreliable estimate of standard error. So which assumption of the classical linear regression model is violated? So ordinary square, whereas ordinary square assume that no independent variable should be a linear function to other independent variable. Recall that each estimation closed loop of the ordinary square regression provide an average value of changes in y for each unit of changes in x holding other independent variable constant. So normally that's how we interpret the estimated coefficient. So we say that when we estimate, so we get beta hat, beta 1 hat, beta 2 hat. So we see that when x1 increase by 1 unit, then y will increase by beta 1 hat, the estimated value, by holding other x to be the same value or remain the same unchanged. So but if there is relationship between x and this x and other x, when this x change the value or increase 1 unit, then other x also will increase the value as well. So that's the problem. So this one, if one of the independent variable is a linear function to other independent variable, hence when its value changes, the value of other independent variable also changes. Okay, the related variable. As the result, ordinary square or s cannot estimate the coefficient of the slope coefficient, beta 1, beta 2, and so on. And although perfect multi-collinearity may exist in theory, it seldom occurs in real world. Example of perfect multi-collinearity is when the researcher has assigned the same variable twice in the model. So let's say you mistakenly, when you estimate, for example, in abuse, you mistakenly type the same variable. So let's say you have x1, y space c space x1, and then space x1 again, the same variable you include twice. Okay, or you have the same in X matrix, you have the same values, the same value of variable. For this one, the first x, and then the second x also the same variable, the same values and the same values. So you have this one exactly the same. Then you have perfect cardinality lah. You have perfect multi-cardinality. And another example is in the case of dummy variable when all dummy variable included is known as dummy variable trap. Okay, so we haven't discussed. I think in week 8, now it's chapter 09, week 8, or after midterm break. I think after midterm break. Sorry, after midterm test. Week 11, week 10, now it's chapter. We will discuss dummy variable, the use of dummy variable to represent the effects of different categories. So dummy variable is just a value one or 0. So let's say you have a variable representing the income of different individuals, so male and female. So let's say you have 100 individuals, some of them male, some of them female. So you want to measure how the salary or income differ by gender. Then you can create a variable, the one that we call as dummy variable, to represent different gender, male and female. So we can have so male and female, we have two categories. So we can create dummy variable for male, and then we also can create dummy variable for female. So dummy variable just value 1 or 0. So let's say you create dummy variable for male, and then meaning that the value is supposed to be 1 if that person or that observation belong to male. Then you put 1. Okay, so meaning that here your values, let's say this is the income or salary. Okay, and then you create dummy variable. You have intercept here, beta 0 intercept. I hope you understand now why we have 1 for the first column. We have 1 in the first column in the X matrix because we have the intercept beta 0. Okay, so let's say the first x1 is dummy variable for male. So let's say you create a variable to represent whether this observation belongs to male or not. If it belongs to male, then you put 1. If not, you put 0. That's dummy variable. Okay, that's what we call dummy variable. If A is equal to 1, if the situation exists or condition exists. If not, 0. And then we also can create dummy variable for female at the same time. We also create dummy variable for female. So let's say if the first observation belongs to male, then this one supposed to be 0 lah. Okay, and then if let's say second observation has is female, then the first dummy variable is supposed to be equal to 0, and then this one 1 lah, because this one dummy variable for male, this one dummy variable for female. Okay, the x1 for male, x2 for female. So what happens when you include dummy variable for all categories? What happens? The sum of the values for all dummy variable will be equal to the first column equal to 1. So this one, so either let's say these two columns x1, x2, these two columns x1 and x2, both are dummy variable. First for male, second for female. So either one can be equal to 1, the another one must be 0 lah, right? Because this person cannot belong to both categories. It must be either male or female. It cannot be both. Okay, so let's say the first person can only be male or female. So either this equal to 1, and then the second person also the same. So the sum of dummy variable, if you include dummy variable for both categories, so what you have, the sum of this and this equal to 1, all equal to 1. You can imagine lah. Understand lah? Can I imagine? And say you have a model. So just again, so your Y, let's say income or salary, monthly salary. So you want to measure, or you want to construct a model that allows us to see the difference between salary for male and female. So we create dummy variable. Dummy variable just value 1 or 0. So your x1 dummy variable for male. So meaning that the value of male. So let's say this one is x1 is for male. So it is equal to 1 if the observation belong to male, okay, and 0 if not. So we can create another variable for female, dummy variable. So let's say x2. If let's say the first observation belong to male, this one equal to 1, this one must be equal to 0. It cannot be 1 for both. Then that's a weird person lah. Have both genders. Okay, so this one, let's say second person, second observation, y2 this salary, this one salary, monthly salary, y1, y2 for second observation, second person. Let's say this person, second one is female. So we have 0 and 1 lah. Right. Dummy variable can only take two values, 0 or 1. So let's say the third one is female again. So you have same 1, the next one male. So you have x1, 1, x2, 0. So this plus this, what happen if male plus female? The dummy variable, x1 plus x2. So you have 1, 1, right? So this is equivalent to the first column. Okay, remember we cannot have any linear dependency within this column, this matrix X. So that if let's say you create dummy variables, and then you include dummy variable for all categories, and then the sum of all dummy variable will be equal to 1, which is equal to the first column. Okay, the first column for beta 0. Remember, the first column all equal to 1. We have all equal to 1. Why? Because we have beta 0 and intercept among intercept. So that when you multiply beta 0, you get beta 1. So that's the problem. That's what we call a dummy variable trap. Dummy variable trap is a situation when we include dummy variable for all categories. So let's say you have 4 categories. Let's say you have season. Let's say you have. Okay, let's say you have education level, educational background. So let's say you have 3 categories. Primary school, secondary school, tertiary. So you have 3 groups. You have 3 categories, and then you can create 3. You can do the same lah. So you can create that variable for 3 categories. For primary school, those who have on up to primary school, secondary school, tertiary, university. So the same lah. So each of the person can only have 1. Can only be equal to 1 for any of the category. The highest educational level highest. So the same lah. So you take sum of them, 3 categories, 3 dummy variable. You take sum of them equal to 1 at least, which is equal to the first column. So normally, so later we will discuss in detail when we discuss about dummy variable. When we want to include, if we want to include dummy variable for different categories, we should not include dummy variable for all categories. We should exclude 1. Okay, let's say for male and female, you just need to include 1 now, either male or female. You cannot include both. If you have normal intercept, okay, so the normal practice is that we have the intercept, but we exclude 1 of the category. Dummy variable, we exclude 1 of the category. Okay, we can have all categories, but we cannot have this one. If let's say you decide to include both male and female dummy variable, so what you need to do, you have to make sure that there is no any other column equal to the sum of them. So how to do that? You have to exclude the normal intercept. If let's say you don't have intercept, then okay lah, because you don't have the first column for everyone. But the normal practice is that we have the intercept, and then you have to exclude one of the category dummy variable, you do not include dummy variable for all categories. Otherwise, you have sum of the dummy equal to 1. All equal to 1. Okay. So now the normal practice is that if let's say you have two categories, you just include two. Let's say just now you have the highest education level. So you have primary, secondary, tertiary. So you just put two lah. So primary and secondary. So let's say you have three categories. So you just include two. So let's say the first person is has the highest education level is primary. And then 1. This one 0 lah. This one secondary school. Okay. And then let's say the second one it has secondary school. And then let's say the third one has tertiary. So both 0 lah. Okay, both 0 because you exclude the tertiary one. And then meaning that when you take some of them, not all equal to 1, some of them equal to 0. So you don't have the problem. You don't have linear dependency between this and the first column. Okay. So that's the normal practice. We do not include dummy variable for all categories. We take up one. Okay. That one we discuss more detail in the lecture 10, no mistaken. We got dummy variable. So that's what we call as dummy variable trap. When all dummies is included. Okay, I mean all dummy, all categories. So this one dummy variable for all categories. Okay, so let's say you have two categories, you include dummy variable for both categories. You have three, you put all the three. And then you have what we call as dummy variable trap. So it's possible to have perfect modality. You have this kind of situation now, so you have exactly the same values appear in different variables, and then you have exact values, and then you have what we call dummy variable trap. Okay, and it is common to find imperfect multimodality in economics modeling as some of economic variables move in the same direction or systematic manner. Example, an increase in the interest rate by central bank will trigger changes in the bond value. All these variables are in stock market as well. So meaning that when the variables that we have in the model, they are moving to the same direction, then we can have what we call as imperfect collinearity between the regressors, between independent variables. So there are a number of effects of multicollinearity. Whenever we have perfect multicollinearity, then we are not able to get estimate of the non-release square. So later we do an example lah. So when we include, let's say you mystically include the same variable in the model, then you will not get. Or maybe we can take example lah. So this one, the example that we are going to use for this lecture lah. This one we have. So this one just an example, you don't need to do. So let's say now we have a model, we want to construct a model to estimate consumption, and then we have two regressors, independent variables, income and wealth. So let's say you mistakenly include income twice, then you have perfect collinearity, and then you will not be able to get estimate lah. For example, if you type, no need to do just to show example. This is just an example. Let's say you mistakenly include the variable twice, your x1 and x2, that's the same variable, and then the third one. So it says that near singular matrix. Okay, so main defect basically is perfect collinearity because you mistakenly include the same variable twice in the model. So you have x1 equal to x2 lah, because x1 exactly equal to x2. So why we cannot get the estimate? Because you recall that the way that we calculate you remember the formula that we used to estimate to get the estimation, this one. So when there is perfect causality, then the inverse of the x transpose x not exist. Okay, so we are not able to get the calculation cannot be done. Okay, the inverse of x transpose x not exist when there is perfect causality between independent variables or between different columns in the X matrix. And then bigger value of standard errors resulted in wider confidence interval, hence the t-statistic becomes smaller. So recall that the formula that we use to calculate t-statistic is just the estimated value of coefficient minus half the size value divided by standard error. Remember that one? Where did we have that one? Okay, I recall this one. The formula that we use to calculate the statistic is the estimate of the coefficient minus half the size value divided by standard error. Okay, the standard error. So the presence of multi-causality will make the standard error to be larger . Okay, it will make the standard error to be larger. The presence of multi-causality, imperfect lah, perfect we will not be able to estimate. Imperfect causality, when there is imperfect causality, then the standard error here, this one, is going to be larger as compared to when there is no multi-causality. So when this is larger, then our t is going to be smaller. Okay, so when something divided by something bigger, then the whole thing, the t-statistic is going to be smaller. Okay, smaller when t-statistic is going to be smaller, then there is tendency that there is the tendency for us to do not reject analysis. So t, you imagine t distribution, so t becomes smaller. So meaning that it has more tendency to for us to do not reject the null hypothesis, because t is smaller than critical value, we do not reject. Imagine the t distribution. Okay, so when t is smaller, then so less likely to reject the null hypothesis because it's smaller than critical value. Okay. So that's one of the implications. So meaning that although in reality it's supposed to be significant, but because of the multi-causality, it makes our estimate to be insignificant. So that we make conclusion, the conclusion that we make based on the Harvard testing is incorrect or not reliable. Okay, because of the multi-causality, we conclude that the X has no significant impact on Y. But that happened because of the multi-causality problem. Okay, the impacts of multi-causality. And then the estimator is sensitive to any changes plus or minus a few sample size, mid to sample size of insignificant variables. So when we have this problem, so normally if you change the sample size, you add more variable observation, then it will have significant change to the estimate, the value of estimate for the certain parameters. And then number 4, estimate has wrong sign. So although we expect to be positive, but after we estimate we get negative. Later we see example. So we have an example. You see that because of the causality, multi-causality, then we get estimate of the parameter with different or incorrect sign. It's supposed to be positive, but we get negative because of the causality, multi-causality. Alright, so to check for multi-collinearity, there is no specific test is available for checking multi-collinearity. This is because in any regression with more than one independent variable, we will have a small degree of multi-collinearity. Hence, the checking is based on how big or how serious the problem exists. Okay, so if the problem is so serious, which make the estimate to be incorrect or to be not reliable, then we have to do something. Otherwise, we can just ignore the problem. So how to detect? So there are a number of ways that we can use to what we call that to identify if there is the problems of collinearity, how serious, if there is serious problem of multiplicity. So we have a number of different ways that we can use. The first one by checking the correlation between independent variables. So let's say you have 3x in the model, then you just check cross correlation between x1 and x2, correlation between x1 and x3, between x2 and x3. Okay, that's why we got pairwise correlation between explanatory variables. So one method to check for multiplicity is to look at the correlation coefficient between the two independent variables. As we know, the correlation lies between -1 and +1. So the nearer the value of correlation coefficient to -1 or +1, the bigger is the existence of serious multi-collinearity between independent variables. So this is useful to see the possibility of having collinearity between two independent variables. But it's not really useful if the linear dependence happens between more than two variables. So let's say for example this one lah. So x1 plus x2 equal to x3. If x1 equal to x2, then we should be able to see that the possibility of having collinearity between x1 and x2 by looking at the correlation between x1 and x2. But if the linear dependency happen or exists in between three or more than two variables, then meaning that the use of correlation not really suitable or not really useful to give us a warning that there is a possibility of collinearity between variables or independent variables. And then the second one, if you inspect the result of estimation and you see that the large overall F statistic for testing usefulness of predictors but small or insignificant T statistic. So you inspect the F statistic that represent the overall significance of the variable of the slope parameters. So let's say that I explained to you before, you recall that the F test statistic we use to perform joint hypothesis testing for all slope parameters in the model. Okay, beta 1, beta 2, beta 3. And now this is all equal to 0, alternatively at least 1 not equal to 0. So normally when we have multi-collinearity, then we have contradictory between F test and T test. So for example, it's possible that F test suggests that at least one X to have significant effects on Y dependent variable, but when you perform the individual testing, then you see all are insignificant. So that one of the indication that the model suffer multi-collinearity problem. Yeah. And then another way to check is by looking at the VIF, the variance inflation factors. If the value of the VIF, variance inflation factor, large, then it indicates for the presence of serious multi-collinearity problem. Okay. So variance inflation factors (VIF) is used to measure multi-collinearity by regressing one independent variable to the other independent variable. Subsequently, for each regression, calculate the VIF with the formula VIF equal to 1 over 1 minus the coefficient of determination. So R square, 1 minus R square, 1 over 1 minus R square will give us what we call as VIF, variance inflation factor. Take note that the R square used in the above formula comes from the auxiliary regression, means that we regress each of x against other x. So let's say you have 3x, and then you regress x1 against x1, x1 against x2 and x3, and then you do again, you repeat, you regress x2 against x1 and x3, and then you repeat again, you regress x3 against x1 and x2. So generally, researchers believe that VIF, the value of VIF greater than 10 show the existence of serious multi-causality. So this one depends lah. I mean, certain book says more than 5, but some book says more than 10. That can give us what we call that just the value that when there is high possibility that there is a serious multi-causality problem exists or appear or present in the model. So the variance inflation factors can be thought of as a ratio of the estimated variance of the estimator, okay, the beta, to what the variance would be with no correlation between independent variable in the equation. So R square of 1, if let's say you regress any of x against other x, any of the regressor of independent variable against other independent variables. So you get it equal to 1, then indicates perfect multi-causality produced